Hello, today we're going to look at a couple other integration techniques, but to get our brain going, I'd like you to try the warm-up and check back. The answer should be 2 times the natural log of 2 plus 3. So see how you do. Hit pause and then come back. All right, let's look at this one. For this technique, we don't have a quotient rule for antiderivatives, so we've got to do something different. Hopefully you remember that one of the techniques we have is just to simplify whatever we have in there. So in this case, I would probably take and rewrite everything with its own denominator. Which means that this is going to be the integral from 1 to 2 of x plus 2 over x plus 3 over x squared. And I can take each of those antiderivatives separately. So x would just be x squared over 2. Did not leave you enough room to write, sorry. Plus 2 times the natural log of the absolute value of x. Plus, this one would be actually minus 3x to the negative 1, or negative 3x to the negative 1 with that sign. So probably I'd bring that down, but I'm going to evaluate this from 1 to 2. So with 2 plugged in, we would get 4 over 2 plus 2 times the natural log of the absolute value of 2 minus, that would be 3 over 2. And then I'm going to evaluate it at 1. So I'd get 1/2 plus 2 times the natural log of the absolute value of 1 minus 3 over 1. So this would give me 2 plus 2 times the natural log of the absolute value of 2 minus 3/2 minus 1/2. That will end up working in my favor. Minus 2 times the natural log of the absolute value of 1 plus 3. Combining like terms, what do we know about the natural log of 1? It is 0. So combining any like terms, here I've got a positive 2, here I've got a negative 3/2 minus 2. I'm sorry, minus 1/2, which gives me a negative 2. So 2 and negative 2 cancel out. This turns to 0, and so that's where I end up with 2 times the natural log of the absolute value of 2 plus 3. Well, we already know 2 is an absolute, or is positive, so I don't really need the absolute value symbols anymore because 2 is a positive number. Great. Okay, so that's a quotient. But what happens if my quotient doesn't simplify the same way? So we've looked at the product rule for integration, basically integration by parts. Let's focus on some quotients and what we might do. Okay, so what I'm going to do, the one technique I'm going to use is I'm going to do long division. So if I can't simplify, meaning I can't factor, I can't reduce it like we did up here, I can't do anything to cancel out any common factors, then what I'm going to do is long division. Okay, let's review long division with polynomials. So the first thing I'm going to do is I'm going to make sure that what's underneath the division symbol has all of its degrees. So if I have an x squared, I also have to have an x and then a constant term. This one's not a problem. I have all my terms here. And then outside, I'm going to write x squared plus 2. Now remember, what we're going to do is we're going to take just this first term, x squared, and we're going to see how many times it goes into x squared. It goes in 1 time, and then I'm going to take and multiply what it went in by 1 times x squared to give me x squared, 1 times positive 2 to give me positive 2. And then what I'm going to do is I'm going to change both of those signs. So I'm going to subtract the entire thing. And subtracting the entire thing makes those signs go away. The whole point of doing this is so that this first term cancels out. What I'm left with, though, is negative 4x, and my 2's cancel out as well. So if I were to write this quotient right here, I could rewrite this quotient to say 1, and then I have a negative 4x over x squared plus 2. If I were to combine these two by finding a common denominator, x squared plus 2, x squared plus 2 over x squared plus 2 minus 4x would yield this x squared minus 4x plus 2. I could add those fractions together. I don't want to, but if I get to this point, I have some terms that I can actually take the antiderivative of. The antiderivative of 1 is just x, but then I need to work on this antiderivative of 4x over x squared plus 2 dx. So how am I going to deal with this? Well, to deal with this one, I'm going to need to try my techniques. Can I simplify it any other way? Can I do a u substitution? If I can't do a u substitution, can I do integration by parts? So go down the list of those techniques, and I'm going to try a u sub here. If we let u equal x squared plus 2, then du would be 2x dx. I want a 4x dx, so I'm going to multiply both sides by 2. So 2 du equals 4x dx. So really what I have is 2 times the integral of 1 over u du, which would give me 2 times the natural log of the absolute value of u plus c. But I'm going to go back and substitute that in with the other one. So we had x, I rewrote the x, minus, this would be 2 times the natural log of the absolute value when we let x be x squared, or sorry, u be x squared plus 2. Plus c. So this would be the answer to that antiderivative. All right, that's using long division. So I would like you to hit pause, try example 2, see if you can come up with the answer. And if you like to know the answer ahead of time, keep watching for a second and I'll write it up on here. If you don't, hit pause and then try it. All right, this answer will be x cubed over 3 minus x squared plus 3x minus the natural log of the absolute value of x minus 1 plus c. So hit pause and see if you can solve that. All right, let's use our long division. I'm going to make sure that what I'm dividing into has all of its terms. X cubed minus 3x squared plus 5x minus 4. I don't need to add any zeros terms. I don't need to account for any. So x times what gives me x cubed? Well, x times x squared gives me x cubed. X squared times x gives me x cubed. X squared times negative 1 gives me negative x squared. I'm going to subtract both of those, change the signs. That should give me 0x cubed. That was the point. This gives me negative 3x squared plus x squared. So I've got negative 2x squared, and then I can bring down my other terms. Now I'm going to repeat that process. I'm going to see how many times x goes into negative 2x squared. It goes in negative 2x times, meaning negative 2x times x is negative 2x squared. Negative 2x times negative 1 is positive 2x. And then I'm going to subtract both of those or change the signs. When I do that, I'm left with 3x minus 4. When I bring down that negative 4, and I know that x can go into 3x positive 3 times. So 3 times x is 3x. 3 times negative 1 is negative 3. When I change both of those signs, I'm left with negative 1. And so I can rewrite this integral to be the integral of x squared minus 2x plus 3 minus 1 over x minus 1. That's my remainder, dx. And now I need to integrate that. Well, x squared would go up a degree, divide by a degree. Negative 2x goes up a degree and divides by the degree. 3x goes up a degree and divides by a degree. But this one will be negative natural log of the absolute value of x minus 1, now plus the c. So that's just a technique. If I don't have a way to simplify my antiderivative, I'm going to use long division to try to break it down. Unless u sub works. Maybe we try u substitution and it works. I would suggest not trying integration by parts on these. I think it would be really messy, but there you have it. Okay, so let's look at some trig integrals. Let's review what we know, and then we're going to talk about a few that we don't know yet, but are soon going to find out. All right, we already know the antiderivative of sine of x is negative cos x plus c, is what I was trying to write. We know the antiderivative of cosine of x is sine of x. Secant of x is tangent of x. Cosecant squared of x is negative cotangent of x plus c. Secant tangent is the secant of x plus c. Cosecant cotangent is negative cosecant of x plus c. Those ones you should know. Now, we have not talked about our inverse trig integrals, meaning what happens if I want to take the antiderivative of something, or what is the derivative of arcsine? What is the derivative of arctangent? We really haven't focused on those. There are two primary ones. I'm going to give you three because three could be used, but the ones you will see most often are the ones for arcsine and arctangent. Okay. If we take the integral and my integral is 1 over the square root of a squared minus u squared du, or du over, then this is going to become arcsine of u over a plus c. Okay, a couple things about this. The a that is listed in here, in all of these problems, the a that's listed in here, happens to be a constant. And the u that is listed in here, this u in any of these problems, and you can tell for several reasons because it says du, this has to be my variable. Now, this u I'm going to use variable loosely, because really it could be a function, and it could be another function with respect to whatever variable we're dealing with. So maybe instead of just x, it's 2x, or maybe instead of just x, it's x plus 5. And that's what we're going to look at. So u is either a function or a variable. All right, so how do we recognize this? Well, we will see something that is a quotient, but doesn't fit the patterns of a long division problem, or doesn't fit the pattern of something that we could simplify any other way. It doesn't look like an integration by parts, so we can't simplify it. So probably the most basic one would be something like the integral of 1 over 100 plus x squared dx. I will tell you that I'm going to rewrite this to be 1 over 10 squared plus x squared dx. And we can see that that fits the pattern of arctangent, where my constant is 10 and my function is just x. And so then this would be 1 over 10 arctan of x over 10 plus c. That would be the antiderivative. Okay. Well, you know they can't be all that easy. So let's flip the page and try a couple. So far, does this fit any pattern that we've seen? Could I simplify the fraction like we did on that warm-up problem today? And the answer is no. I couldn't rewrite this anyway. Could I factor this denominator and maybe there's a common factor in the numerator? Well, no, because nothing multiplies to 9 and adds to 4. Could I do long division? Well, no, because I'm x squared never goes into 8. So it doesn't, this is the remainder. This is all that's left. So what can I do? What I'm going to do, since this doesn't fit any pattern, is I am going to use completing the square. I'm just going to abbreviate CTS. I'm going to use completing the square to write the denominator in factored form. Okay, so what does that look like? Do you remember the process of completing the square? We're going to start with this x squared plus 4x, and my goal is to add something to that to make it a perfect square. But I can't neglect the fact that there was already a plus 9, and nor can I just add something to a polynomial without also subtracting it from the polynomial. Otherwise, I've changed the problem, and I don't want to do that. Remember, to complete the square, we take our b term and we divide it by 2, and then we square it. So in our case, we would do 4 divided by 2 squared, which gives me 4. I'm going to add 4, and I'm also going to take 4 away. And if you remember, now what we have is this creates a perfect square trinomial, meaning the same two binomial terms multiply together to give me that. And what multiplies together is x plus 2 squared. And you could check that if you want. But when I then add the plus 9 and the minus 4, we get plus 5. If you wanted to, you could expand this, and you should end up with x squared plus 4x plus 9. Okay, well, why does this help me any? Well, let's rewrite this integral to be the integral of 8 over, I'm going to put it in a slightly different order. I'm going to write 5 plus x plus 2 quantity squared dx. Why might I do that? Well, hopefully what you notice, let's maybe make one more rewrite. If I pull the 8 out and I write this as root 5 squared plus x plus 2 squared dx, does that look like something we had on the front side? This is an arctangent. This too is an arctangent function. Now my constant is root 5, and then the variable or the function that is in it is x plus 2. So the antiderivative here would be 8 times 1 over root 5 arctangent of my function is x plus 2 over root 5 plus c. And this would be my antiderivative. All right. I threw a little trick at you in example 5. Would you hit pause and try example 5? Try completing the square, noticing it doesn't fit any other pattern, and come back and see if you can do the antiderivative. And if you would like to wait to see the answer first, give it a second before you hit pause. All right, the answer you should get is arc sine of x plus 3 over 7 plus c. Now hit pause and try it. Okay, hopefully what you remember about completing the square is two things. One, if we have a leading coefficient, we should pull it out. So looking at this denominator, the first thing I'm going to do is I'm going to factor out that negative. This will make it a positive x squared plus 6x. I still need to add something, but then I have minus 40, and then I'm going to take something away. I'm still going to go through and do my b divided by 2, and I'm going to square it. So in my case, it'd be 6. My 6's and my b's look an awful lot alike. 6 divided by 2 squared, which would be 3 squared is 9. So I'm going to add 9. I'm also going to take 9 away. Knowing that that negative is still out front, I'm going to factor the perfect square trinomial, which would be x plus 3 squared, and then I have minus 49. Now keep in mind this is all underneath the radical, so I'm going to go change it in just a second. But do you notice that then with that negative sign, when I distribute it, really this becomes 49 minus x plus 3 quantity squared. Okay, so let's rewrite the integral. This would be the integral then of 1 over the square root of 49 minus x plus 3 quantity squared dx. If it helps you to see it better, we can certainly rewrite that 49 to be the square root of 7 squared minus x plus 3 squared dx, and that fits my arcsine formula where my a value is 7 and my u, my function, is x plus 3. And so this antiderivative is just like what I wrote down there, is the arcsine of x plus 3 over 7 plus some constant of integration. So those are two more techniques, more of the quotient rule type. Sometimes we have to use long division and sometimes we have to use completing the square. And we cannot neglect that sometimes with fractions, it's just simpler to change them a little bit. Rewrite them as individual fractions or see if you can factor out terms. Sometimes that's a good technique too. So good luck with the assignment today and let me know if you have any questions.